Good afternoon, everyone. Welcome to Graduate Thesis Talk Series. This is our second event of the semester. I am very honored to present and having this conversation with all of our students. I'm Arash Soleimani. I'm a professor and chair of graduate studies at Woodbury University. So I'll be presenting today. The title of presentation is Computational Design Thinking, Insights from Designing with Algorithms. So I'll be actually, during my presentation, refer to the book recently I published with Routledge. Came out a couple of weeks ago. This is a textbook since past, 10 to 15 years I've been teaching computational methods in different institutions. I felt always this lack of a textbook teaching computation, mathematics, programming, and design in the design programs. So that was the intention of putting together this book. So it's a collection of a lot of experimentations in the classrooms, doing research, students' work, and I'm so happy that this finally came out. So we will have, followed by this presentation, a book launch. We have some limited copies, so I'll provide more information after we finish. But in terms of presentation, overall, the format, first, I would provide some foundation work like intellectual framework, what is algorithmic thinking, what is computational thinking in design. And then I would like to show this computational thinking integration in classroom settings, projects, different areas of the design curriculum, and showing you some different students' work, because I think it's very important, especially for our thesis students, to look at a variety of projects. So I'll be showing some examples, and then followed by some design research projects, collaborative work with other colleagues across other institutions, and ending with some snapshots from the book. But throughout the presentation, I'll be referring back to this book as well. Okay, computational thinking is a way of getting to solution through a clear definition of steps needed. So in a lot of design schools, there is great emphasis on presentations, graphics, realistic renderings. As a critical designer, I'm more interested in to know about mechanisms, algorithms, steps, processes involved. So this term computational thinking has been defined across different disciplines, from architecture, biology, mathematics, computer science. There is some sort of commonality in those definitions, which consider computational thinking as a way of solving problems, designing systems, and understanding human behavior using concepts from computer science, and dealing with a lot of abstraction, automation to solve a problem. So I'm going to show you a lot of examples today. I hope when you leave after this presentation, you have an idea what computational thinking is. Something I want to say, computational thinking is not necessarily the machine. It's more about the process. This is one of famous computational thinking examples, the Tower of Hanoi. So the challenge here, we have 5 disks and we have 3 pegs. So how many minimum steps we need to move all those 5 disks from one peg to another, by knowing that you cannot put a larger disk on top of a smaller disk, and you can only move one disk at a time, right? So I'm sure that I can see you started moving things around. It looks like a very straightforward process. Anybody wants to take a guess how many steps we need, minimum steps, to move all these 5 disks from one column to another? Sorry, I'm behind in the slides. So I'm dealing with 2 computers. So this is the Tower of Hanoi. So we have 5 disks. We want to move all these 5 disks from one column to another, but you should know that you can only move one disk at a time, and you cannot put a larger one on top of a smaller one. Very straightforward process, right? I see hands moving around, heads moving around. So you're moving things around. Anyone wants to have a quick guess? We had a 12 here. 15. The answer is 31. okay? So there are many steps involved, okay? Even though the process is very straightforward, if you had this tool at your hand, you could have solved it easily. But there are steps involved, okay? This is an example of recursive thinking. So the steps are interrelated. To solve the next step, you need to know about the previous steps. Even though this is like a very straightforward, easy task, but you need to go through steps. As a critical designer, sometimes we use text-based programming, just creating like a simple if loop to answer that question. And sometimes we use visual programming just to document the steps. And when you go through that, you will notice, oh, there is the pattern here. So we did 5 disks here. So how about if you have 6 disks? How about we have 7 disks? And when you start doing that and like having fun with Tower of Hanoi, you will learn that this is the basis for a lot of fractals. So how fractals are generated. So this could have been one full presentation by itself today. But if you're interested, I really encourage to go and study. There are a lot of research about this. Okay, so more examples. I am a puzzle collector. I have tons of puzzles. And these are some of the examples. We do composition, decomposition in design a lot of time. So you do precedent studies. You decompose a building to understand the logic behind it, understanding the steps behind it. So I'm trying to tell you how important the process is, even when you're solving a puzzle. So these puzzles, the first step is to separate these pieces from each other and then putting them back again together. So that would be a second puzzle. And they have different difficulty levels. I brought one of them with me today. It's that infinity puzzle, which is my favorite. So get here, she's having fun with it. She's trying to solve it. She's almost there. Good to know that. So what I like about this one, because you cannot solve it accidentally. So you really need to understand the logic behind it. So when you play around with it, like me, spent 3 weeks to understand that, you will notice there are 2 gear systems within this. We are getting close to solution, Gadir. There are 2 gear systems. When you play around, you will understand there's some mathematical logic behind it.
Can I explain it? I already know what it is.
Please go ahead and explain it.
Really?
Just a few words. Tell us, what did you learn about a puzzle?
Okay. So there are 2 pieces on the right. There's 2 rings inside the infinity piece, and one of them, I'm 2 steps in actually. There are some divots that you have to turn and make the shape. Because there's quicker. Oh, sorry. You have to twist and turn, but there is an internal divots that you have to match the shape in order to twist it out and then pull and twist.
Very good. That's the idea. But in practice, when you play around with it, like for 3 weeks, you will learn that there are numbers here, or there is a pattern. So there are 2 gear systems. Basically, you have to rotate one step and then rotate clockwise the other one 360 to release one step for the left one. And then going backward anti-clockwise to release another step. And you continue that until you release 2 gear systems. And then you will notice that there is a mathematical logic behind it, even to solve a puzzle. I went too fast. So that's just an example of computational thinking, thinking about the steps and trying to understand the steps. Here is a comparison by Mark Gross from Colorado Boulder from some years ago. He compared these 2 words, I'm pretty sure everybody's familiar, program and design. So when you break these words and try to understand the definitions, so both the first parts, pro and d, mean something out, forward, off, whereas gram and sign means something written, mark. So design has always been computational. And we all have been programmers then, and computational thinking is not different from design thinking. And, excuse me. Design has been always computational, and this is not a new idea. I want to show you some classic examples. What you're looking at On the left-hand side, this is Chartres Cathedral from 1220 in France. So this great cathedral was not built by accident or randomly. They didn't say it's cool to have windows up there. They actually generated an algorithm. And they designed algorithmically, systematically. And this represents a way of thinking computationally from a long time ago. Or the other example, on the right-hand side, this is San Galgano Cathedral from Italy from 1218. This shows different layers of abstractions and how to use those abstractions to create a system and the building language. Let's take a look at a contemporary example. This is Stata Center at MIT by Frank Gehry. So this building was designed by a lot of computational tools, 3D geometry, NURBS, and you couldn't do that without mass customization of panels, double curvature, and a lot of computational techniques. To be more concrete, I'm going to show you another example. So this is basically a setup in another institution for a coffee station to make a coffee. And I'm a coffee fan, so I have to drink a lot of coffee. So when I was going there to make myself a coffee, I mean, this was like a routine order, grabbing cups, milk, coffee, sugar, lid, napkin, and leaving the space. Imagine if you walk with someone in that tiny space, so it makes it even more complicated. I'm not going to say this is the best solution, but just think about if we move the lids to the other side, right? So this can save us a lot of time. So the way I think about design, it's more about a system rather than being an object or a building, a system of design. So when you design a project, you're not designing a floor plan, basically. You're looking into what are different ways that you can arrange that room or put the furniture around. Maybe that's the way we measure capacity for spaces. So you remember the previous example. So how many different ways we can create this flow and organize these pieces around the room. And so once you accept the idea of designing a system, it takes you to consider that design as exploring constraints, defining constraints for your project. The more you learn about the design project, the more you apply constraints. And this is actually how problem and solution co-evolve. Okay, let's look at another example. This is one of the initial examples I introduced in computation classes. I ask students to think about one of their routine tasks. So here, we're making a sandwich, right? So even it's a very automatic, intuitive process to think about how you make sandwich, slicing through the bread, slicing through cheese and tomato, and thinking about the orders, right? So when you think about the steps and processes, actually the next slide, if you have some experience with any programming like Grasshopper, Dynamo, just think about some of these components that you use in Grasshopper. You deconstruct the geometry, the input, you pick the right items, you put them in right order, and you make something happen. So this is very similar. So basically, these are examples of computational thinking. This changes the way that we think about problems. And you become more critical about design steps. And you know that this can get fairly complex by adding more parameters. You remember the more parameter constraints you define, the more closer you get to a more defined design solution. So this is one of former students' final thesis project. She was studying sound and wind as like driving forces for the design process. And doing the investigation of how those parameters can be defined as design parameters directly informing the final design project, which was a performative skin system. This is a table from the book. So when you introduce computational thinking or this method in your design process, it helps you to create a system. So in a conventional design process, we do a lot of sketch storming, which will end up to a design project. However, when you think computationally and use computational tools during process, you need to think about parameters. You need to think about rules to create a system, and you end up with design solutions instead of one design. And this is the loop, so you can go back and define or change some of your initial parameters to get different design decisions. Okay, so speaking of algorithmic thinking, so we need to know about some definitions, ingredients, parts of an algorithm. So each algorithm is made out of multiple constituent parts, process, start, and end nodes. This is like a common thing in making algorithms. Decision nodes are the one that when we want to make a decision in a design process, there's always a start and end nodes, and also lastly connectors. That shows the process flow for the algorithm. So these are some basic concepts about how to craft an algorithm. Now, I want to show you one specific example, a research question. That's something I encourage all thesis students. Always think about questions. Posing good questions is really important because research questions are the one direct your study. So if you don't have questions, so then what is the research? So research always is built on top of proper research questions. So this is one simple question. How can a facade system be programmed to be adaptable, responsive to the sun path? Like a very simple concept. How can we design an adaptable skin system responsive to sun path? So going through some of the things that we looked at, if you want to design a solar responsive facade, so obviously we have this starting point for the script. And then as a designer, you still need to design, let's say design a reconfigurable module that offers different configurations. So this is an example. So a module that offers closed, semi-closed, and open configurations. Okay, so then now asking, okay, what is this? What is the season that this skin system is operating? So how do we measure the season, or how do we measure sun angle, like altitude angle? So measuring the angle, and then also there are different configurations of that skin system, and this is like a kind of not one-way path. It can go back, and we can revise and optimize the script, and this can get more complex when you introduce like horizontal sun path, like azimuth angle into it, and adding more parameters. But I just wanted to show you one example. When we talk about algorithm, they're not heavily computationally written. This is something you can just brainstorm. Think about the steps and processes. Okay, and these are some configurations. So when you figure out, when you make that system, it doesn't give you one solution. You look at a variety of solutions, and you choose the one that best fits your project. Or in this example, it could be like an operable, reconfigurable system. Okay. So one other terminology is in design by using computation is parametrics or parametric design. So parametric design is an approach to design process using computational thinking. Obviously, when we talk about parametric design, we need to ask, okay, what are the parameters? So in a lot of classes with students, I have a lot of discussion. What are design parameters that we can use and benefit during the design process? I listed some examples here from mathematical parameters, geometric parameters, topological parameters, representational parameters. When you use Revit, for instance, a brick wall, representation parameters could be the number of bricks, for instance, or the color of the bricks. Material parameters, environmental parameters, structural parameters, and human parameters. So it's all about asking questions, be precise, and documenting your data collection and use them during your design process. Okay, and a good practice to learn computational logic is just to decode existing building. So look for different examples. These are some examples. This is Randall Museum working with like wind flow. So what good examples is just to build existing building and create a design system. So that work with different wind patterns. Or this is there's a kinetic facade system. So asking yourself, how can I decode that? What is this responsive to? What are input parameters in this example would be like? And how can you program that? It's a lot about practicing. Or this is one ocean pavilion. This performative skin system opens to sunlight. So it's responsive to solar behavior. And then asking yourself, how can I program that? So what is the driving force? Asking this question and also doing, you don't have to necessarily start a very complex project. Or here's another famous project, Al Bahar Tower. So this skin modulation, they open and close to accept or reject light. So big part of that is just to getting out of the comfort zone and start experimenting and modeling some existing building and creating design system. And sometimes just experimenting with the tools that you have, like rotational synergy, playing with grid systems, creating different grid variations, or even using agent trailer for agent-based simulation, modeling, or just painting. Okay, so that was the first part of the presentation, theoretical foundation. So next, I want to show you how some of these have been integrated into the classroom settings, from classes to thesis projects to a degree projects. When I joined here, I was in charge of developing design computation Bachelor of Science program, a lot of courses in the program, so how this became a discipline. Okay. So a lot of those parameters we were talking about, like structures, environmental system, structures by nature, they are very parametric. From design to doing structural analysis, showing forces imposed of surface system, and considering load conditions across the surface. Or when we design a network system responsive to solar radiation while balancing access to daylight parametrically and creating desired shading systems. Or in this project, the focus is to consider a concept of acoustic in design. I mean, acoustic qualities are not visual, so how can we use something which is not visual as a driving force for the design project? And when we deal with numbers, you can easily implement them in your design project. And sometimes we deal with qualitative data. How do we incorporate this in design project? So always asking questions and thinking, brainstorming about this design steps that you're taking is really important. And this is an example of one of former thesis students. So he studied, analyzed and decoded existing structures in nature and different phenomena to extract underlying logics and algorithms. Or here's another example using simulation tools to generate different design variations for different conditions. One of the studios I've been teaching for some time, and I taught this also last year here, Topic Studio, was programming materials. So working with students, how we can use some very ordinary material, like a thread, and make something extraordinary out of that. So a thread system, it's like very simple. What you're looking at, this is not a rendering, it's a physical model. So thinking about the process, and everything has been handmade. So there's no computer, but in their analysis, they also use computer. Or here's another example of when nature is the source of inspiration, using Cocoon to make structures. Or when mathematical geometric exploration will inform your design process. Or you can use mathematical exploration for form finding as well. Or here's another example of using textile to define rules, parameters, and creating different sort of point and curve attractors, creating different closure systems. Or here's another example of students' work when mathematical parameters and numbers inform the design process. And here are more examples of experimenting with different mathematical equations, how they can be visualized, creating different conditions and spatial qualities. More examples, and this becomes like the final physical model. Again, this is not a rendering, so this is like a physical model, and you can create sometimes forms that you cannot make out of ordinary material. So you cannot make this out of concrete, you cannot make this out of brick. So material, understanding material behavior, and material programming is a big concept in computational design. This is a former thesis project by a student. She used this inspirational hand sketch and developed that comparing human lungs to building skin. So the way we use our lung, comparing to building skin for filtering different environmental qualities. And these are some of her analysis, research, learning about how buildings can contribute to air cleaning capacity. And some detailed section drawings. She studied how to maximize the surface area through a modular design and different tessellation techniques to increase exposure to sunlight, which contributes to the air cleaning capacity when it's coated with titanium dioxide. So you can see it's a very simple concept, but it can give a lot of direction in your design project. And her final project focused on like an open source experimental education and research center. Okay, the third part of the presentation. So now I'm going to show you some research products, research publications, funded projects, collaborating with different colleagues across the world. So the first project, and also students. The first project I want to show you is, this was the funded project in another institution. I worked with a group of undergraduate students advancing research. We work together to design interactive kinetic structures responsive to different environmental conditions. And you can see actually they were all undergraduate students. They co-author and we published the paper together. One of the projects I wanted to walk you through was solar cell. Solar cell was developed by studying patterns found in nature, like the cellular structure, to create aperture systems sensitive to light. And the way it was built we were using Arduino microcontrollers so they can sense different light quality variation, and this can open and close. At the same time, there are photovoltaic cells embedded in the cells, so we can harness energy and we can turn on the lights. So here's a short video, shows some of the processes when students were experimenting with like computational form-finding processes, pattern development, using a lot of machineries that you also use, like vacuum forming machine, fabrication tools, 3D printers, and getting also to the final concept model when this kind of mimics flower behavior using Arduino, which is a microcontroller. You can integrate a lot of sensory activities and make your built environment more responsive. Yeah, these are some study models, and this was one of the final prototypes. And there were multiple other projects came out of that project, like intersecting cog, which was completely like a manual interactive system, as in like entertainment system. You can, like a lot of these puzzle in a museum setting, you can go and open and have fun with the, or the one on the right-hand side, breathing skin, so that mimics water flow in a building skin system, again using Arduino. And in previous institution, I initiated a lab, design analytics lab. So this was a wall as part of that lab. So it became like a culture in design programs. So these kinetic structures were being built in different studio project classes and were showcased every semester. So these are some of the examples. And I know this is continuously being the culture, and these are just some examples from some years ago. The next project I want to show you is, again, focusing on a kinetic structure. This is a work with Dr. Alani from Tuskegee University. So we explored different structural systems that are automated to allow different shape-shifting structures. So imagine you live within a space. That space is not static, is interactive, is responsive. It will shape-shift based on your needs and desire. So we have been publishing multiple papers, and this was a funded project as well at Human-Computer Interaction International. This is another paper we published a couple of years ago. And what you see here, there's a lot of sensory here that recognizes human body. And imagine you can program that wall to grow or shrink. So imagine if this becomes the building scale. So I have a short video, just going to let you watch, shows some of the processes. And we had a lot of students work with us to develop this system. We use Arduino and Kinect to make these interactive systems. And this is a continuing line of research. We published a paper last year into Barcelona and presented the paper. So we're more focusing on the AI learning aspects of the machine system. So the next project I want to show you, this is another collaborative effort with a colleague, structural engineer, Dr. Loreto. So we've also been publishing a lot of paper. And you can see now computational thinking comes into structures. Structure is a lot about parameters, numbers. In this particular line of research, we've been investigating fabric formworks to create concrete products, like a beam structure, like a column, or any structural systems. So I want to show you like a very simple example. So you're all familiar with like a standard grid system, columns and beam system, concrete system in structure. And I'm sure you know the graphic representation for a structural system, and you are familiar with, if you're not, you will learn about those. What is a moment diagram? What is a shear diagram? And we learn a lot of these things, and we say, okay, that was a structure class, we're done. But what really matters, how we can apply this to a design project. So this here, I mean, the concept is very simple. You have moment diagram, shear diagram. You have to design in a way that the building reaches equilibrium. So how about if we just overlap those diagrams and let that diagram to inform the design of the beam system, to optimize it. So this is one example of one of the projects that we've developed. So when you have the beam system, so in concrete, the most important thing is how much material you can scoop out, non-working material, to make it more performative. Because once you remove unnecessary material, you're increasing performance, you're making your product more sustainable and more environmental friendly, at the same time becomes more performative. So with this approach, we can scoop out unnecessary material. Right? This is one example. Here in this example, we are removing about 30% weight of the concrete. Just imagine how much concrete we build, how much heat it releases. So by removing that, we are contributing to our environment. So this is a section, and the other section, when we look at it, the catenary curve can also be optimized. So this project solely focuses on structural member optimization. And we are currently developing a plugin that you can optimize different structural systems, like from a beam system, from a column system, and it creates different configurations. And the last chapter of my book also actually gets into some more details, how to bring enforcements, post-tension into a beam system. And these are some examples. You know, when we think about concrete, we all think about like these rigid surfaces. But concrete is gel. What I love about concrete, you can give any form to this material. So this is a line of research studying how we can use fabric formwork system to make concrete more huggable, touchable. So you experience that structure. So we designed this kind of reconfigurable formwork when you can adjust the formwork and create different structural members. So these are some images of one of the projects that we did. So typical standard material, but using fabric for a portion of the model. And this is one of the iterations, casting concrete, letting it dry, and getting sample tests for structural compressive tests. And this is the final product. Imagine if you design a beam system, not only is it structural, but also it's aesthetically beautiful and it's more performative. And it comes out of like two simple diagrams. And experimenting with different materials to improve the performance, the texture, and quality of concrete surface. And this is the final product we were testing in Georgia Tech lab. Okay. So this is basically, that was the biggest part of the presentation. I have now a couple of snapshots. I want to take a few seconds to talk to you about the structure of the book that I recently published. So when it came out, so basically this is the result of 10 to 15 years of teaching computational methods. But when this came out, I spent like the past 2 years full time just to get this book done. But when it came out, it was like real baby. So I was waiting for it to come out. So you wait for a baby 9 months. I was waiting for this for 2 years to come out. But I'm super excited for the book. The book has 7 chapters. First chapter is introduction. The next 5 chapters are building mathematical exploration, parametric design from 2-dimensional to 3-dimensional exploration. The last chapter includes multiple case designs. So case design in different disciplines. So my intention with the book is that so if you understand this mathematical computational logic, you can apply that to different things. Not just architecture, not just interior design, not just graphic design, even the way that you dress up, even the way you make things, even the way you live, it affects your lifestyle. So the last chapter has multiple case designs that shows how what you learned in previous chapters are applied to like real world examples, and each chapter culminates with a comprehensive assignment. So when you learn about different concepts, there is like an assignment at the end. And one thing I want to tell you, do not expect any codes or script in the book. There's no code here. It's more about how to generate logics, how to think about process. So with that said, these are some snapshots from the book, case design chapter. So you can see when you learn about algorithmic approaches, parametric design, you can even apply that to typography. So bringing like using different mesh system or kinetic alphabets that are responsive to different inputs. Or here's another example, defining point and curve attractors in a way that we generate new font typologies. So there is a case design focuses on Islamic patterns, and Mukarnas is an Islamic module. It's a architectural module that helps works with transferring load from a ceiling condition to wall system. So how can you parametrically build that? How can you look at different variations? Generating arch system. What happens if you change the arch geometry? Gives you different configurations. Or even in terms of typography, calligraphy, generating forms, patterns. Excuse me. Or in this example, how can we do different weaving techniques? You can see even we are getting into textile design. So different types of textile and weaving system, how we can introduce different attractor systems. So the nature of that is very parametric. You just need to have fun with it. Or the last the last chapter in case design, focusing on the simulation engines. So how can we use data for simulation, ranging from wind simulation, light simulation, sound simulation, acoustic simulation in the built environment. And the studio I'm teaching this semester, having a lot of fun with architecture, media arts, and design computation students. They're building on top of this part of the presentation. And I want to conclude with 5 takeaways. So I know I showed a lot, so all around. But I at least want you to remember 5 key things, 5 ways that we can change the way we work. We already talked about thinking algorithmically, computation. It's not necessarily the machine. It's about a process, the way you think about a problem. So think algorithmically. Alternate. These days we live in a world that you are exposed to so many different tools, software, platforms. So instead of making one design, you can make hundreds of designs. Think about different design variations and then choose the right design out of them. So this helps you to optimize your projects. Datify, use data to inform your design. I'm sure we all have been doing site analyses, program analyses, but make it more tangible. Automate. You can use a lot of tools to automate unnecessary steps. So to save time and shift your focus to somewhere else in your design process. And also evaluate. So when you create a range of design solutions, you can use a lot of evaluative tools, simulation engines, to optimize or choose the best design solution with your list. And I think this is the last slide. And thank you, everyone. I'm happy to take questions. I just want to tell we have limited copies. I think we have 18 copies here. It's like first come, first serve. The actual price for the book, I think, is $55. Thanks to Dean's office and Galina, they helped to purchase these books at a discounted rate, 30% discount. So it's about $34.49 or $38.49. So if you are interested, so there is a QR code, so you can sign up, and I'm happy to sign your copy. With that said, I'm open to take questions now.